Thank you. So thank you for the invitation. I'm very glad to talk here. And yeah, I will talk about barcodes. And more precisely, I will try to find another way to construct barcodes with more dynamical tools. So just to remind, what the barcode is, just basically a set of intervals, finite and semi-infinite intervals of R, which are called bars. And the main purpose is to represent persistent modules, which are, we can keep in mind that a persistent module is just a filter homology, like Morse homology, Floer homology, etc., etc. And so when you take the homological definition of the barcode, the first example you want to compute is generally the barcode of a Morse function. So let's just take a Morse function defined on the do sphere like that. And what we want to do is to look at the sublevels of our Morse function h and how sublevels include into higher sublevels homologically. So we just do the filtration, and by doing the filtration, we obtain some bars depending on what happens on the homology. So the homology will change at the critical values of h, and then we will obtain two kind of critical values, which will be the birth points, where we just those are the values where some homology is created, and the day spawns where the homology is killed in some sense. And then we obtain some bars like that with this example. So in symplectic geometry, so the notion was introduced by Polterowicz-Luking and Scherzang. The barcodes in Floer homology are defined by the Floer homology. So if we consider Hamiltonian function defined on, for example, here a surface, because I will only work on surfaces for this talk, we just take the filtration of the Floer homology given by the action functional, and then we obtain a filtered homology, which is a persistent module, and then we obtain a barcode. What is important in the barcodes, the Floer homology barcodes, is the fact that the endpoints of the bar are actually the values of the spectrum of H. The barcode is a conjugacy invariant. It is continuous in some topology. It extends to some homeomorphism. So it's a really nice object to study and to understand, like, the spectrum of Hamiltonian functions, like etc., etc. And my purpose was to understand how to construct barcodes for homeomorphisms here, because with the definition of Floer homology, we can extend it to homeomorphism by taking some limit of barcode of diffeomorphisms. But with the limit process, it's like we don't really understand what happened to the limit, to the barcode we obtain at the limit. So my goal was to find another way to construct barcodes for Hamiltonian homeomorphisms without using Floer homology and without using at least a C2 setting, for example. So just to remind everyone that a Hamiltonian homeomorphism for a symplectician is just a limit of Hamiltonian diffeomorphism. But in more symplectic point of view, we can think as a Hamiltonian homeomorphism as the time one map of an isotopy, where the flux of this isotopy through every loop is equal to 0. So it is Hamiltonian homeomorphism of surfaces here. So it's just a good dynamical way to interpret this kind of object. Okay, so now we will always consider a compact Oriented surface. And every Hamiltonian homeomorphism will have a finite number of fixed points in this talk. So with Floer homology, we construct the barcode by taking the filtration of this homology by the action functional. So we need at least an action functional on homeomorphism. And thanks to the work of Wang, this function exists. So for every Hamiltonian homeomorphism with a finite number of fixed points, there exists an action function defined on the set of fixed points and which extends the classical notion of diffeomorphism. So just to give you an idea on how this action function is constructed, like if you consider two fixed points of f, which are fixed by an isotopy, the difference of action function between those two fixed points is equal to the flux of the isotopy through every path joining those 2 points. So the main problem is that if you consider two fixed points of f, you may not find an isotopy fixing both of those fixed points. So it's more complicated, and you have to consider isotopies on the universal cover of the surface to reconstruct the action function. And it remains some difficulties remain to construct a barcode. Is that we have no function defined everywhere. Like for example, in the Morse case, we have a Morse function defined everywhere, so we can consider the sublevels, and so we compute the filter homology of the sublevels. For Floer homology, we have a Hamiltonian function defined everywhere, and here we just have a Hamiltonian homeomorphism of a surface. So I needed to find another way to construct barcodes, and it's why I created an application which associates to some graphs barcodes. And those kind of graphs are actually couples GA, where I consider G a finite oriented and connected graph, and A will be the action functional, which is defined on the set of vertices and which is decreasing along the edges. So now, how to find this kind of graphs? So for example, if we consider again the Morse function at the beginning on the two sphere, we can choose a Riemannian metric. We can consider the gradient lines of H. And from these gradient lines, we can define naturally a graph on the left part, where the set of vertices of my graph will be the set of critical points of the Morse function. And we can decide to put an edge between two critical points if their difference of index is equal to 1, and if there is a gradient line joining both of them. And so with this graph and the action function defined by H, the Morse function, with my application, I obtain a barcode. So the barcode actually depends on the Riemannian metric and the gradient lines of H. So there's a
sorry, I don't understand. So your edges, do they have multiplicities? So if I have several gradient lines between two critical points, I have several edges in the graph.
Yes. Actually, you can, with the way it's constructed, you can choose you can choose to put edges between every fixed point if there is at least one gradient line.
So for you, 1 or 2, it does not matter.
No, it doesn't matter, because actually what I do, I do a filtration of the graph, and I'm looking at the connected components of the subgraphs. So it doesn't matter if I choose to put edges between critical points of index difference of index equal to 1, or if I don't care about the Morse index.
Okay, thank you.
And actually, no, you're welcome. And actually, we can prove that the barcode I obtain does not depend on the choice of the Riemannian metric, and actually only depend on the Morse function, and is equal to the barcode we obtain from the Morse homology. So now, okay. So if we consider again a Hamiltonian homeomorphism of a surface with a finite number of fixed points, we have, thanks to the work of Wang, action functional defined for this Hamiltonian homeomorphism, but we still need to find a graph to apply my application beta to obtain a barcode. And those graphs come from Le Calvez theory and Le Calvez positively transverse foliations. So the main result of Le Calvez is way more general. It states that for every maximal isotopy, there exist foliations positively transverse. So every maximal isotopy of homeomorphisms, I don't need a Hamiltonian homeomorphism to obtain this result. And I will explain briefly what every word means in this statement. So we consider an isotopy from identity to our homeomorphism F. We set the set of singularities thing of I, which are the set of fixed points of F, which are actually fixed along the isotopy. So it is a subset of the set of fixed points. And we say that this isotopy is maximal if this set thing of I is maximal for the inclusion. So we can prove that if we consider homeomorphism, there exists in general a lot of maximal isotopies. And for every maximal isotopies, Le Calvez proves that there exists a topological foliation, a C0 oriented topological foliation on the set on the complementary of thing of I, which is positively transverse, meaning that for every point which is not a singularity, the path of this point through the isotopy may not be positively transverse to the foliation, but it is positively transverse to the foliation up to an isotopy relative to the end. So on the left, I drew like the trajectory of a point, which is not positively transverse, but we can find an isotopy to transform this path into a path which is actually positively transverse to the foliation. And the main fact that I will use, if we consider again a Hamiltonian homeomorphism, we know that we can find a maximal isotopy for this Hamiltonian homeomorphism, and every foliation given by Le Calvez theorem is actually gradient line, meaning that we can consider the leaves of the foliation as gradient lines of a gradient function, of a function like a Morse function, for example. And an important fact is that the action functional is actually decreased along the leaves of the foliation. So be careful. Here, the action functional is not defined everywhere. It's only defined on the critical points and the singularities of the isotopy. But since the foliation is gradient line, we can really represent the foliation as a gradient of a Morse function. So we are close to define a graph because we have the same kind of drawing as previously with the Morse example. And then for every foliation, I can define a graph where the set of vertices is equal to the set of the singularities of the isotopy, sorry. And I put an edge from X to Y if there exists a leaf from X to Y. So here I don't actually care about the index, the Morse index, or Conley index of my points. And what we saw earlier is just that the graph is naturally equipped with the filtration given by the action functional A of f. And so with the application beta, I can construct barcode. So summary, if I consider Hamiltonian homeomorphism and I fix maximal isotopy, Le Calvez theorem gives us some foliations. From this foliation, we can define a graph, and with the application beta, I can obtain a barcode. And the first result is the fact that the barcode actually does not depend on the choice of the foliation and only depends on the choice of the isotopy and the homotopy class of the isotopy, exactly. So to prove this theorem of independence, I actually had to create another kind of barcodes. And I define an order on the set of singularities for a maximal isotopy. So now, let's forget about foliations and just consider maximal isotopy of Hamiltonian homeomorphism.
Excuse me, and could you please remind what is maximal isotopy?
A maximal isotopy is just, it's an isotopy such that every fixed point of f, which is not fixed by the isotopy, is linked with the singularity of the isotopy. So for example, if
which singularity?
If I consider like just put this, consider it's a Hamiltonian, autonomous Hamiltonian. Okay, so everything just turned around like the point z, and the natural isotopy is a maximal isotopy, because if there is another fixed point, like for example, if z is a fixed point of f, it is linked with the other singularities here. So you can't find an isotopy fixing every singularities S1, S2, X1, X2, P1, P2, and the point Z. You have to make a choice if you want to see Z as a fixed point of the isotopy. Is it clear, or?
Does it mean something on the universal cover of the complement of the point somehow? Does it say something about the lifting of the isotopy?
Yes. I will. You will see it just after with the definition of the order. We can have some good ideas on what happens. Okay, so to prove the independence of the barcode, I need to actually define another kind of barcode, where I define an order on the set of singularities of the isotopies. Let's just consider a maximal isotopy. And for two singularities of this isotopy, I say that x is greater than y if, so I take a surface, I consider two singularities of the isotopy, x and y, and if there exists a path gamma such that on the universal cover, on the complementary of the set of singularities, this path lifts into a path which is a Ruhr line, I say that x is greater than y. So what is a Ruhr line? It's just that the image by a lift of f tilde of gamma is on the left part of gamma tilde, and the pre-image of gamma tilde by f tilde is on the right part of the path. So where does it come from? It's just that now for this maximal isotopy, with Le Calvez theorem, I can consider a foliation which is positively transverse, and actually every leaf of such a foliation lifts into a Ruhr line. So if we consider it just in some sense generalized the idea of the foliation, because now I just can consider local leaves, and I don't need a full foliation defined everywhere on the surface. So a good thing is that the action function decreased along the order, meaning that if x is greater than y, then the action of x is greater than the action of y. And then I can construct again a graph which only depends on the isotopy. So I set G of the order, the graph where the set of singularities, the set of vertices, sorry, is again the set of singularities of the isotopy. And I put an edge from x to y if x is greater than y. So again, it is naturally equivalent a filtration, and with the same, I obtain a barcode where the barcode depends only on the maximal isotopy. And the first result is the fact that now this barcode is equal to the barcode I obtain by considering positively transverse foliations. So it proves the independence of the barcode on the foliation given by Le Calvez theorem. So the main problem is that if I consider Hamiltonian homeomorphism, I need to fix maximal isotopy, and for every maximal isotopy, I can construct barcodes. But so the natural question is, can we construct barcodes which depend only on F and without to consider an isotopy? And another result is that because at the beginning, what I wanted to do is to find another way to construct barcodes, but I want to actually find the Floer homology barcodes of my Hamiltonian homeomorphism. And the barcodes I constructed are actually equal to the Floer homology barcode in the simplest case possible. So if we consider C2 closed Hamiltonian diffeomorphism, such that the fixed points are non-degenerate, so everything is perfect. We don't need to choose a maximal isotopy, because in this case there is a unique homotopy class of a maximal isotopy fixing every fixed point of the Hamiltonian diffeomorphism. Yes, because I ask the number of fixed points to be finite again. And in this case, the barcode I constructed is equal to the Floer homology barcode. And so the main question is it more general, and can we find a way to construct dynamically barcodes for Hamiltonian homeomorphisms with those kind of tools? And I have some ideas where I want to use torsion law isotopies, but because of some Conley-Zinder index problems, I need to actually, maybe I will have to use some kind of generalized torsion law isotopies defined on the universal cover of the surface. So thank you for your attention, and I will be glad to answer any questions.
Thank you very much. Thank you, Benoît.
Thank you.
Indeed, we have 6 minutes until next talk starts for questions. So are there any questions?
Maybe.
Can you? Sorry.
Okay, go ahead.
Go ahead, Leonid. Maybe it's the same question.
I just was confused with the correspondence between Morse functions and barcodes via graphs.
Yeah.
Because what confuses me that, for instance, if you have a surface which is not simply connected like torus,
Yeah.
So then you simply kind of see critical points of index difference 1 with, let's say, 2 gradient trajectories, and it's nice to record them or something like this. So, I don't understand how you choose edges. Could you please repeat this?
Actually, it just comes from the definition of this application, because what I do is just I have graph with a filtration, and I filter the graph, and I'm just looking at the connected components of the graph. At every time of the filtration, actually I have a partition of the critical points in the graph, and with this partition, I just construct with hand bars for the barcode. So
you said that you can reconstruct barcode in any degree. Not
no. I only do it on surfaces, and I'm working to
on
generalize.
surfaces, but in degrees 1, 0, and 2, right?
Yeah.
In all the degrees, only by looking connected components of the graph.
Yeah.
Okay.
Just for these degrees. Yeah, I'm working to generalize this construction, but I have some kind of problem because I have to choose something in the construction, and it may not be natural to. So it's still work in progress.
Okay, thank you.
Welcome.
For the, can I ask a question?
Yes.
For the case of area preserving homeomorphism, do you distinguish? Yeah. Do you distinguish periodic orbits or fixed points which are contractible and non-contractible? And is that connected to the singularities? Is there something there? Because usually Floer homology, Floer homology should give you different persistence modules depending on whether your periodic orbit is contractible or not. And do you see that in this case? And is it connected with the?
For now, I only see a contractible fixed point in periodic orbits, because because every fixed point on periodic orbit I can see are actually fixed by at least one maximal isotopy. So it has to be contractible to see it as a singularity of a
this is the only ones you see?
Yes.
So could it happen that some contractibles one you don't see, or the fact that it's maximal is equivalent to saying that the orbit is contractible for some lift?
It's a difficult question I'm trying to answer, actually, because the problem is, if you consider just a singularity which is contractible, you can find a maximal isotopy which fixed this fixed point.
But not all of them together, maybe.
Yeah, not all of them together. It's not possible because of the Convezinder index. Actually, because what you can see with maximal isotopies is so the set of singularities, either it is torsion law, so it's the right Convezinder index, it's -1, 0, and 1, or 0, 1, 2, it depends on the convention.
I'm afraid we're going to be interrupted because it's time, but maybe we can discuss that.
Yes, if you want.
Yes, exactly. This is what I was starting to say. So thank you very much, Benoît, again.
Yeah, thank you.
And